For part 2 of lecture 10, we're going to call this lecture 10b. We're going to look at more alpha substitutions and condensations. The first reaction that we should look at is the Claisen ester condensation. The Claisen ester condensation is a lot like the aldol condensation, except we're going to use esters instead of aldehydes or ketones. I want to point out that compared to a carbonyl like acetone, whose pKa at its alpha carbons is about 20, an ester at its alpha carbon has hydrogens with pKa's of about 24. So esters are a little bit less reactive at their alpha site, meaning that if for some reason we ever had an ester and an aldehyde or ketone in the presence of a base, it would be the ketone that's more likely to have its alpha carbon deprotonated, and therefore the ketone that's more likely to be the nucleophile. The ester, because we have two O's on the carbon, actually makes the carbon a better electrophile. So if we have a mixed system here with a ketone slash aldehyde or an ester, the ketone will be the nucleophile and the ester will be the electrophile. But in the Claisen, it's ester plus ester. So we'll use a base to remove an alpha hydrogen from the alpha carbon. That will get us an ester enolate. It's exactly the same as the regular enolate that we saw last time, except that we happen to have an OR group next to the carbonyl. So this C- can be delocalized onto the O-. We can use that ester enolate as a nucleophile to add to another ester. But remember that esters are a class of that special carbonyl, that when we form that tetrahedral intermediate, the electrons will come back down off the carbonyl and displace the OR group. It won't displace the carbon-carbon bond that we just formed because O- is a better leaving group than C-. So we'll do our attack from our alpha site onto the carbonyl, make our alpha-beta bond, get the tetrahedral intermediate, that will collapse, kick off that OR group from the ester, and what we're left with is a beta keto ester. This is a new type of product. With aldols, it was beta hydroxy or alpha beta unsaturated. With the Claisen, it's a beta keto ester. There's a beta carbon, beta to our ester is a carbonyl, a ketone carbonyl. So it's a beta keto ester. That is the type of product that you will make from the Claisen. Here's a trick. As we're learning these reactions, I want you to identify the reaction by the type of product that it makes. Think about what kind of product the aldol makes, what kind of product a cyclic aldol makes, what kind of product Claisen makes. That way, when you look at a product, if you can identify that pattern, you can associate it with the reaction, and that will help you figure out how to make that product. So the same way that we had a cyclic aldol, which was an aldehyde or a ketone adding to itself in an aldol reaction, we have a cyclic ester Claisen condensation as well. But instead of calling it a cyclic Claisen, it's called a Dieckmann ester cyclization. So the same way that we had two aldehydes or ketones on the same molecule for the cyclic aldol, we have two esters on the same molecule for the cyclic Claisen. So using a base, we can remove a hydrogen from our alpha carbon. That alpha carbon will attack the other ester group, displace the electrons onto the O. That gets us a tetrahedral intermediate, which will collapse. And when it collapses, we'll regenerate the carbonyl and we'll generate the beta keto ester. In this case, though, because it was a one molecule and intramolecular reaction, we end up with a cyclic product. Here's an example where instead of making a 5-membered ring, we make a 6-membered ring. In either case, because this is a Claisen, we just call it a Dieckmann, but because this is a Claisen condensation, we'll always get the beta keto ester as our product. Like we had a crossed aldol, we can also have a crossed claisen. Sometimes crossed clasins refer to having two different esters, the same way that the crossed aldol had two different aldehydes or ketones. But a crossed claisen could also refer to a reaction where you have a ketone as your enolate and the ester as your electrophile. So in that case, you'll have a 1,3 diketone. A crossed claisen where you have two different esters will just be like a regular claisen, where you have a beta ketoester. But if you have a ketone or aldehyde as your nucleophile and the ester as your electrophile, that's also called a claisen. We just call it a cross claisen, and your product will be a 1,3 diketone. We actually saw the cross claisen on the very first slide of the first part of this lecture. That's where I introduced you to the idea of using a enolate as a nucleophile with various electrophiles. There's another class of reactions involving alpha carbon nucleophiles called Michael additions. These are also sometimes called more generally conjugate additions. In a Michael addition, you have an alpha beta unsaturated ketone, which, by the way, note well, is the product of an aldol. The alpha beta unsaturated carbonyl, in this case it's a ketone, it could be an aldehyde, but the alpha beta unsaturated carbonyl was the product of an aldol condensation, is also a good electrophile, and it has two electrophilic sites. One electrophilic site we can see by delocalizing the electrons from the pi carbon-oxygen bond onto the oxygen, gets us a positive charge on that carbon. We can then move the pi electrons from the alpha beta bond over to get rid of that positive charge and delocalize the positive charge from that carbon onto the beta carbon. So we have two electrophilic sites, the carbonyl carbon and the beta carbon. This means that we can have two sites that our nucleophile will add to. If it adds to the carbonyl carbon, we call that 1,2 addition. So a nucleophile adding to the carbonyl, kicking the electrons onto the O, gets us an O-, in which we can then just protonate to get to an alcohol. We call that 1,2 addition. That is the standard type of nucleophilic addition that we've always seen to our carbonyl groups. That's what we did with a Grignard or a lithium reagent, or all kinds of nucleophiles that we've added to our carbonyl. They've all been 1,2 additions. In fact, the aldol and the claisen are all 1,2 additions because they're adding to the carbonyl carbon. If we add to the beta carbon, though, which remember in the event that we start with an alpha beta unsaturated carbonyl, we can also add to the beta carbon. That we call 1,4 addition or conjugate addition, and this is specifically what we call Michael addition. So here our nucleophile adds not to the carbonyl carbon, but to the beta carbon. In that case, the carbonyl adds to that carbon. That swings these pi electrons over one slot and kicks the electrons up onto the O. The fact that the nucleophile adds to the fourth atom in this conjugated chain and the electrons end up on the first atom of that conjugated chain. See, the nucleophile is, say, on the 1 and the oxygen is on the 4, or the oxygen is the 1 and the nucleophile is the 4. The fact that the two atoms that participate in this reaction are the 1 and the 4 in this chain, we call it 1,4 addition or conjugate addition. From that point, if we protonate our carbonyl, look what we get. We get an enol, an alcohol on our carbon-carbon double bond. And since enols are unstable, they will tautomerize to the ketone form. So notice that the O in the carbonyl is a carbonyl in our starting material and in our product. It's as if the carbonyl did not participate, although in the mechanism we see that the carbonyl clearly did participate in this reaction. It served to receive, ultimately, the electrons that were displaced when the nucleophile attacked our beta carbon. here, just zooming in, the book highlights that the O that ultimately gets the electrons and the carbon that gets the nucleophile are in a 1-4 relationship to one another. That's why we call this 1-4 addition. And in the 1-2 addition, the carbon that gets the nucleophile and the oxygen that gets the electrons and ultimately the hydrogen are 1-2 to one another. So the question then is, how can we control which site the nucleophile adds to? If we start with a alpha beta unsaturated carbonyl and we introduce a nucleophile to it, how do we know or how do we control which carbon the nucleophile adds to? Well, it requires a special type of nucleophile to do the 1-4 addition. The type of nucleophile that it takes to do the 1-4 addition is something that we call a Michael donor. And the electrophile specifically has to have that alpha beta unsaturated group. So we call that a Michael acceptor. The nucleophile is the donor because it's donating the electrons. The electrophile is the acceptor because it's accepting the electrons. And the type of this reaction is the Michael addition, the conjugate addition. So let's look at what Michael donors look like. Michael donors will be cuprates, lithium dialkyl cuprates. Remember, we saw cuprates before in the ketones and aldehydes chapter. If you don't remember, go back and look at what the cuprates did. Cuprates were a special type of organometallic nucleophile that would add only once instead of twice to acid chlorides and esters. These were kind of weaker versions of Grignards. Other Michael donors could be an enamine, where we have electrons on nitrogen that are conjugated with a carbon-carbon double bond. We could have a beta diketone. Look at all these: beta diketone, or beta ester, or beta ketone nitrile, or alpha nitroketone. These are all enolates or cousins to enolates because the negative charge and electrons on this carbon can be delocalized onto adjacent carbonyls. We've got a carbonyl here that can take the electrons, carbonyl here that can take the electrons. In the beta ketoester, we've got the carbonyl on the left and the ester carbonyl on the right. On the beta ketone nitrile, the carbonyl on the left and the nitrile on the right. Either one can accept the lone pair, delocalize the electrons onto the O or the N. In the alpha nitroketone, we can delocalize the electrons either onto the carbonyl on the left or the nitro group on the right. Remember, we saw in the electrophilic aromatic substitution reaction, the nitro groups are good withdrawing groups. In fact, all of these are withdrawing groups. All of these groups on the right and the left withdraw electron density from the carbon minus. Our Michael acceptors could be any conjugated alpha beta unsaturated carbonyl. So a conjugated aldehyde, conjugated ketone, conjugated ester, conjugated amide, conjugated nitrile, a conjugated nitro group. All of these could accept a nucleophile to the beta position. Beta, 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 beta. All of these are beta positions relative to our withdrawing functional group. So in order to get a 1,4 addition, you need a Michael donor and a Michael acceptor. Now, one thing to note here is that all of these Michael donors are nucleophiles that are stabilized by something. These are weaker nucleophiles than usual. The dialkyl cuprate is a weaker version of the Grignard or lithium reagent. And all of these Michael donors are highly resonance stabilized enolates. They're not normal enolates. They're doubly stabilized enolates. They're stabilized by not only one carbonyl that makes them enolates in the first place, but another withdrawing group. So the question is then, why is a weak nucleophile the type of nucleophile that adds 1,4? It then implies that other nucleophiles, like Grignards or lithium reagents, that are stronger will add 1,2. We've always seen that these strong nucleophiles that we use with carbonyls add 1,2. but these weaker nucleophiles add 1,4. Now, why is that? Let's go back and look at our two mechanisms. This is a similar concept as the idea of kinetic versus thermodynamic control. It's not kinetic versus thermodynamic control, but it's similar in concept. Notice that in the 1,2 edition, we have an O minus, and in the 1,4 edition, we have an O minus. But think about where the double bond is. In the 1,2 edition, the double bond remains in the alpha beta position. And look at the level of substitution on our double bond. Our double bond is mono-substituted in the 1,2 edition. The only group on our double bond is the carbonyl. And that is true throughout the mechanism. But in our 1,4 edition, the double bond moves. It gets to move from a less substituted position to a more substituted position as a result of the nucleophile adding into the beta position. So, with strong nucleophiles that are highly reactive, we don't care so much about what our product looks like. Think about the nucleophile being so reactive that it doesn't care that the double bond gets left out over in this less substituted position. If our nucleophile is less stable, it can be more thoughtful. It can be more considerate to the double bond and move it over. The nucleophile is not so selfish. It's not so reactive. That's a way you can remember 1,2 edition with strong nucleophiles versus 1,4 edition with weak nucleophiles. When you have a weaker nucleophile, you have a lower energy in your system, you will go through a lower energy pathway. If you have a higher energy nucleophile, you'll have a higher energy system and you'll go through the higher energy pathway. I had a student a few years ago who made a funny kind of analogy to this, said, imagine that you're walking down the street and you have to go to the bathroom really badly. If you have to really go to the bathroom badly, you're going to jump into whatever restroom you can find, even if it's dirty. If you don't have to go to the bathroom that badly, you might take your time and walk a few more blocks to a clean bathroom. If you are a strong nucleophile, you are going to try to find whatever bathroom you can and get rid of your electrons. You're going to donate your electrons to whatever you can find, regardless of how stable or unstable your product is. That will always be the 1,2 pathway. If you are not desperate to get rid of your electrons, you can spend more time and eventually attack your beta position and go through a more stable pathway. So kind of a silly analogy, but if it helps you remember it, it's good enough. So our weak nucleophiles will be Michael donors, and they will only be Michael donors if you have a Michael acceptor to accept them. If you don't have a Michael acceptor or you don't have a Michael donor, your other options are to have a strong nucleophile that will go 1,2. The last reaction that I want to look at today is called the Robinson annulation. Annulation is just a fancy word for ring formation. Here's the Robinson annulation. Here's the big picture. We start with a carbonyl and an alpha beta unsaturated carbonyl. Now again, notice that this is a Michael acceptor. This is the product of an aldol reaction. And in this reaction, we are adding a ring. We're starting with one ring, and we're creating a second ring. Therefore, it's a Robinson annulation because we're making a ring. Now, this is a pretty interesting reaction. It almost looks like we're snapping this 4-carbon chain onto our original carbonyl. But notice that the carbonyl moves. We've got a double bond in there. So let's look at what's going on here. It's kind of an interesting reaction. It's an interesting mechanism because we've seen every single step of the mechanism. The mechanism, you can think of it as being in 2 parts. The first part is a Michael addition. We're going to use our ketone as a Michael donor. This is a stabilized nucleophile because that electrons can be delocalized onto a carbonyl. So we've got our Michael donor. We're going to deprotonate our alpha hydrogen with a strong base. That's going to get us our enolate. And then we're going to introduce it to our alpha beta unsaturated carbonyl. And since we have a Michael donor, a stabilized nucleophile, and a alpha beta unsaturated carbonyl, we can do beta addition, or that 1,4 addition, that conjugate addition. So our nucleophile will add to the beta position, the electrons will swing over. Again, that's into the more substituted position. And then our double bond on our O will swing up onto the O. That gets us our O minus. What will then happen is it will protonate and tautomerize into the carbonyl. So remember, we showed before protonating this O and getting an enol, which then tautomerizes to the ketone. In this reaction, they're kind of showing that tautomerization step where the electrons come down off the O to make the double bond, and then we protonate from the pi electrons and we get to our ketone. It's the same overall picture. It's just a matter of what method of tautomerization you want to show. So we end up with a 1,5 diketone. 1, 2, 3, 4, 5. It's a 1,5 diketone, and that is a classic product that is formed in the Michael addition. In the second step, what we do is an aldol, but it's not just an aldol, it's a cyclic aldol, because we've got one molecule that has 2 carbonyls on it. In this case, it's 2 ketones. We've got the ketone on the first ring, and we've got the ketone that's left over from our Michael reaction. So since we have 2 ketones on the same molecule, we can do a cyclic aldol. In basic conditions, we'll deprotonate a carbon that's alpha to a carbonyl. That will get us our enolate. That will add to the other carbonyl as our electrophile. We'll make that alpha beta bond from the alpha carbon of one carbonyl to a new beta carbon. We'll get the O minus from our carbonyl. That gets us our OH. And again, as always, the product of an aldol is a beta hydroxy carbonyl. In this case, we made a cyclic beta hydroxy carbonyl. Thirdly, we can do a dehydration. That's always an option in the aldol product. If we have any appreciable amount of heat, we'll do a dehydration where our base removes another alpha hydrogen. We get the enolate, and that can eliminate with the OH, kicking off the OH as our leaving group and getting us an alpha beta unsaturated carbonyl. So the Robinson annulation, again, is in 2 steps. It's first a Michael addition, and then the product of the Michael undergoes a cyclic aldol with the dehydration step. Now, here's a good challenge for you. Use this mechanism to figure out how you would get these Robinson annulation products from some starting materials. Your starting materials for the Robinson will always be a enolate or an enolizable carbonyl and an alpha beta unsaturated carbonyl, because your first step is the Michael addition. So the same reactants that are required for a Robinson are also required for a Michael. So maybe work backwards. Start from your product of your aldol in the Robinson and work backwards. Take apart your product and figure out what steps you have to go through to disconnect your product back into the reactants that we use. You've got 2 molecules here to do that. Give it a shot. We'll do it in class. So in case you are too busy or can't figure out how to do it yourself, we'll go through it in class. But it will be beneficial to try it yourself. Now, in closing, I've made a table to summarize all of the reactions that we've seen in this lecture and the previous lecture. I've done a lot of work for you here. I've organized all of your reactions for you in terms of the name of the reaction, the type of reaction partners that we need, the reagents that are required to get those reaction partners to come together, and the type of product that we form. Let's go back and look over these. We've got the aldol first, and we said that's the aldol condensation, the crossed aldol, and the cyclic aldol. All of those are classified as aldols because they are reacting an aldehyde or a ketone with an aldehyde or a ketone. remember that if it's a cyclic aldol, those are on the same molecule. If it's a crossed aldol, those are different aldehydes or ketones. In either case, we need a strong base like NaNH2, and the product will be either a beta hydroxycarbonyl, or if we have heat, the alpha beta unsaturated carbonyl. That's the aldol condensation part, is what happens when you have heat. We did O alkylation and C alkylation. We can control O alkylation versus C alkylation by using either a moderate base like a T-butoxide for O alkylation or a strong base like NaNH2 for C alkylation. In either case, we need an aldehyde or a ketone plus an alkyl halide or an alkyl tosylate. We need a really good electrophile for these reactions. So alkyl halide or alkyl tosylate would be good enough. If we want O alkylation, we use a moderate base. If we use C alkylation, we use a strong base. Now, go back and look at our products. If we did O alkylation, we ended up with a vinyl ether. If we do C alkylation, we end up with an alpha substituted carbonyl, an alpha alkylated carbonyl. We did alpha halogenation, in which we started with an aldehyde or a ketone and then reacted it with a halogen. We could do it under a strong base or a mineral acid. If we use a strong base, we get polyalpha halogenated carbonyl, or the carboxylate if we started with a methyl carbonyl. Alpha halogenation and base, or then we called it the haloform reaction when we started with a methyl carbonyl and ended up with a carboxylate. If we use the mineral acid, we only end up with a mono alpha halogenated carbonyl. That was the end of the first part of this lecture series. Then in this lecture, we did the Claisen, the crossed Claisen, and the Dieckmann. The Claisen was an ester plus an ester. We did that with a strong base, and the product was a beta ketoester. The crossed Claisen, specifically the one using an ester with an aldehyde or a ketone, also required a strong base, but instead of the beta ketoester, we got the 1,3-diketone. The Dieckmann was the cyclic Claisen. I used a diester for that, a single molecule with two esters on it, also using a strong base. We got the cyclic beta ketoester. Any Claisen will be a beta ketoester. We then did the Michael addition, which was a Michael donor, plus the Michael acceptor, which was the alpha beta unsaturated carbonyl. We used a strong base again, and the product was a 1,5-diketone. The Robinson was the same thing. It was the Michael product plus the aldehyde or ketone. We used a strong base, and the product was a cyclic aldol product. That was the Robinson annulation. It was basically a Michael followed by an aldol. So the product looks like it's an aldol. So the trick again is to memorize what products come from what reactants. If I give you a complicated molecule and you can analyze it and say, aha, this is a cyclic beta ketoester, you say, well, then it's a Dieckmann, and our starting material must have been the diester. If I give you a beta hydroxycarbonyl or an alpha beta unsaturated carbonyl in our product, you can say, aha, I can make that with an aldol. If it's attached to a ring, you might think, that's a cyclic aldol product. Maybe it was from a Robinson, which was also involved in Michael addition. So we've got all these different either reaction partner conditions or products to pay attention to. The trick is to keep them straight. Which product can come from which reactant partners, and which reaction partners can give what product, and maybe the reagents matter. Okay, that's the end of our lecture. Again, like last time, this material is in Stromanis Chem Activity 25 and 26.